In this presentation, I talk about marine navigation's core definitions. I show a solution of a traverse sailing triangle that is calculating courses and distances for short coastal navigation. Marine navigation is the art of locating geographic positions at sea and finding ways from one place to another. And traditionally, it required knowledge of astronomical bodies such as sun, moon, planets, and stars, and their movements on the sky. However, with the advent of artificial satellites and modern electronics, it has become more a science of artificial satellites. So basically, there are two modes of navigation at sea. One is a coastal navigation and the ocean navigation. Coastal navigation involves short distances such as along coastline or islands hopping over a limited area of approximately 12 miles radius at sea. The earth may be assumed to be flat for most practical purposes. So due to the curvature of the earth at 50 miles radius, errors are introduced in distances and directions for considering the earth as flat. So these errors are rather minute and not appreciable until about 600 miles. And ocean navigation, on the other hand, involves vast distances for intercontinental and global travels. A passage beyond 600 nautical miles, particularly in the east-west direction, will add considerable distance if using the method of coastal navigation. Besides, the Earth is not a perfect sphere. For ocean passages, the navigation problems are solved using spherical trigonometry and selecting a suitable datum such as WGS 84, that is World Geodetic System 1984, which is used by the artificial satellites. This is a true representation of spherical Earth in 3 dimensions. However, it is not convenient for day-to-day navigation tasks. The shortest distance between 2 points on the surface of the Earth is an arc of a great circle. A great circle is a circle whose center is coincident with the center of the Earth, which actually divides the Earth in exactly 2 halves. A rhumb line, which makes a constant azimuth, that is the fixed angle with all the meridians, is actually a longer distance if considering the Earth as flat and using coastal navigation methods. This picture shows a segment of the Earth as flat on a 2-dimensional graph. In fact, this is misrepresentation of Earth's surface on a map and is using Mercator's projection. However, it is highly convenient for practical and day-to-day navigation tasks. If we notice great circle, seemingly longer distance is the actual shortest distance between the 2 points on the surface of the Earth, and the rhumb line track, which looks like a shorter distance, is much longer distance in real on the surface of the Earth. Before solving an actual navigation problem, let's see the core definitions which are very helpful in this subject. Geographic poles, these are the 2 points where axis of rotation of the Earth cuts its surface. They are the North and the South Pole. Equator is an imaginary line on the surface of the Earth which has equal distance from the North and the South Pole, dividing the Earth into 2 halves. Latitude is an angle at the center of the true spherical Earth between the plane of the equator and a point on the surface. The equator is 0 degrees latitude and the latitude of the poles are 90 degrees. Latitudes are named north or south depending on whether they are north or south of the equator. Parallel of a latitude is an imaginary line parallel to the equator joining places of equal latitudes. Parallels of latitudes are small circles centered on the axis of rotation of the Earth, and they are normally labeled as latitudes on maps. Meridian of a longitude is an imaginary line on the surface of the Earth joining the North and the South Pole, forming a semicircle. Its center is coincident with the center of the Earth. Meridians are normally labeled as longitudes on maps. The meridian passing through Greenwich Observatory in London is called the Greenwich Meridian or the Prime Meridian. It is the 0 degrees longitude. And the longitude is an angle between the planes of 2 meridians, the first passing through the prime meridian and the second passing through a place on the surface. So this angle is the same on the pole at the intersection of 2 meridians. Longitudes are named east or west depending on whether they are east or west of the Greenwich Meridian. So the latitude and longitude of a place is the geographic position of that place. For heavenly bodies, sun, moon, planets and stars, and artificial satellites, it's a position where the body or satellite will be directly overhead. A true track is the angle measured clockwise along a meridian. The reference is taken from the north as 000 degrees. And the last but not the least, the distance c mile. This is 1 minute of an arc of a meridian. That is 1 minute of difference of latitude at the center of curvature of the Earth. If the Earth were a perfect sphere, then it would be equal in all places. The shortest distance on the surface is an arc of any great circle. So this is a nautical convention for measuring directions and distance on the surface of the Earth. Direction on the Earth's surface are measured in degrees and denoted by three-figure notation. The reference is taken from true north as 000 degrees or 360 degrees after a complete turn measured clockwise, that is along the meridian of an observer. Here we see a compass rose printed on most nautical charts from 000 degrees to 360 degrees measured clockwise. So distance at sea, as mentioned before, it is a 1 minute of an arc of a great circle on the surface of the Earth. For practical navigation, the Earth is assumed to be a true sphere using the best fit WGS-84 spheroid with radius equal to 6,378,137 meters. Using the formula 2 pi r to calculate the circumference of a circle, using this formula, we find that 1 minute of an arc is equal to 1,855.325 meters. Since the Earth is not a perfect sphere, it's slightly flattened on the poles and bulged at equator, the mean value of 1 nautical mile is 1,852 meters. This slide shows the graph of the surface of the Earth for calculating true directions and distances. Like any other 2D or surface graph, the Earth also has 2 reference axes and 4 quadrants, and these are counted clockwise from northeast, southeast, southwest, and northwest. The horizontal axis, east is positive and the west is negative, aligned with the equator, and which is the 0 degrees latitude. Scale of horizontal axis. The Earth is round, having 360 degrees on the east-west axis along the equator. So therefore from 0 to 180 degrees east is positive and 0 to 180 degrees west is negative. 180 degrees longitude is called the dateline. The vertical axis is the north and south axis aligned with the Greenwich meridian, which is the 0 degrees longitude. This line is passing through a place in London called Greenwich. And the scale of the vertical axis is measured from 0 degrees latitude equator to the North Pole as plus 90 degrees and from 0 degrees latitude equator to the South Pole as minus 90 degrees. It is very important to understand that the graph of nautical chart is actually drawn on a Mercator's projection. A Mercator chart shows meridians as equally spaced parallel straight lines cutting the parallels of latitudes at right angles. Due to this property, the track's rhumb lines are drawn as straight lines and the great circles as curved lines. In fact, the meridians converge toward the poles. Therefore, to keep the shape of land correct in its immediate vicinity, the latitude scale is gradually increased away from the equator, resulting in gradual enlargement of land sizes as the latitude increases. Due to this property, the polar regions cannot be shown on a Mercator chart. So this slide briefly gives a very important terminology when reporting directions. A true track is actually the intended track between 2 points A and B. If we find our geographic position away from the true track, then we set our course, which is a true direction, to return to the intended track or return to the destination. And that is called a true course. That's the direction in which the ship is being steered. And if we are reporting an object or land or another ship or boat, that is called true bearing. So true bearing is actually the direction in which an object is reported. So the basic and simplest method of navigation is solving a traverse triangle. A traverse triangle is found by traveling on the surface of the Earth, because when an object travels on the surface of the Earth, its coordinates change. So the following directions show an object can travel on the surface of the Earth. So it is the northerly and southerly track. When traveling along a meridian, only the latitude will change, the longitude will stay the same. Another direction is the easterly and westerly track when traveling along a parallel of latitude. Only the longitude will change, the latitude stays the same. And for all other tracks, the object will make an angle theta with the meridian, and that will make a traverse triangle. Both the latitude and the longitude will change. So the change in latitude is called the delat or difference of latitude. So on a northerly changing latitude, it is named as north, and on a southerly changing latitude, it is named as south. Similarly, for the change of longitude, it is called the difference of longitude, and on an easterly changing longitude, it is named as east, and on a westerly changing longitude, it is named as west. So for example, a 30 degrees angle along the meridian in all four quadrants will be measured as 030 in the northeast, 150 in the southeast, that's 180 degrees minus 30 degrees, 210 degrees in the southwest quadrant, that is 180 plus 30 degrees, and it will be 300 in the northwest quadrant, that is 360 minus 30 degrees. So this slide will show a solution of a traverse triangle. The Rhumb line is the most convenient method of day-to-day navigation at sea, and is that a vessel follows a constant track between 2 points from point A to point B on a Mercator chart. The Rhumb line forms the hypotenuse of a right-angled triangle ABC, where the lengths of the triangles are AB is the distance on the hypotenuse, AC is the difference of latitude, that is the adjacent side to the theta, CB is the D long, that is the opposite side to theta, and theta is the true track in three-figure notation. The most important point to understand here is the scales of D lat and D long, that they are not comparable or compatible with each other, because D lat is the arc of a meridian, arc of a great circle, which can be directly measured in nautical miles, and 1 nautical mile is 1,852 meters. Whereas the D long is not an arc of a great circle except for on the equator. This is the only equally graduated scale on a Mercator chart. Therefore, in order to solve the traverse triangle, the D lat must first be converted to an equally graduated scale as of the D long. The converted value of the D lat is called the difference of meridional parts. The meridional parts of a latitude can be found by the following formula. So meridional parts is equal to 10,800, which is 180 times 60 divided by pi times natural logarithm of the tangent of 45 degrees plus latitude divided by 2. So meridional parts formula is derived using calculus, that is integration of trigonometric functions, and which will deserve its own video in the future. Now that we have all the values, D lat in nautical miles and D long and DMP in comparable scales, we can find the tangent theta by D long divided by DMP, which is opposite divided by the adjacent, and the distance uses the cosine theta, that is the hypotenuse divided by the cosine of angle theta. On this final slide, we will solve a practical question. We are given geographic position A and B, and we need to find true track and distance from A to B. So there are 3 steps involved. We take the Mercator chart. Step 1, we find the D lat, D long, and DMP using the given geographic positions, and we draw a traverse triangle. Once we have the traverse triangle, we find the true track using the trigonometric ratio function of tangent theta. So theta is the tangent inverse, D long divided by DMP, and we convert this theta to 3 figures notation. And then step 3 is we find the distance in nautical mile using the distance D lat divided by cosine of theta. So in this example, we solved a very simple one-track solution. A passage may involve multiple tracks. For a small passage could be 3 or 4 legs, or a longer coastal passage could be 30 to 40 legs. So for every single leg, we need to find the course and distance, and we build a table. And from that table, then we work out for every single point our alter course position, distance to go, what is our speed, and based on the speed, we know what will be our ETA, and there will be some variations like currents, wind direction, some variation from the true track, and set and drift. So lots of elements are involved. But this was the most basic method of solving the traverse triangle using latitude and longitude.